Right now, more than 800 million adults on Earth are living with diabetes. That is roughly 1 in every 10 people alive today. And for most of human history, a diagnosis of the most severe form of this disease was not a chronic condition to manage. It was a death sentence, and a slow, wasting one. Doctors watched patients shrink to skeletons over weeks, unable to do anything but watch the clock. Then, in the span of about 18 months in the early 1920s, a small team working with borrowed lab space and slaughterhouse pancreases turned that death sentence into a daily injection. This is the story of how that happened, and why, a century later, the same drug that saved millions is still out of reach for some of them. The earliest known written description of the disease comes from ancient Egypt. The Ebers papyrus, a medical text dated to around 1550 BCE, describes a condition marked by the passing of too much urine, a symptom so strange and specific that it stood out enough to be recorded, even though nobody understood what was causing it. Independently, physicians in ancient India arrived at the same observation from a different angle. Around the 6th century BCE, the physicians Sushruta and Charaka described a disease they called madhumeha, or honey urine, after noticing something almost impossible to miss once you looked for it. Ants and flies were drawn to the urine of certain patients as if it were sweetened. Sushruta went further, distinguishing between patients who developed the condition young and thin from those who developed it later in life while overweight, a split that, thousands of years later, would turn out to be medically real. The disease got its name from ancient Greece. Around 230 BCE, the physician Apollonius of Memphis coined the term diabetes, from a Greek word meaning to siphon or pass through, describing how patients seemed to pass fluid straight through their bodies without retaining it. The Greek physician Aretaeus of Cappadocia, writing in the 2nd century CE, gave one of the most vivid clinical descriptions in ancient medicine, portraying the disease as a kind of internal dissolution, flesh and limbs seeming to melt away into urine. He considered it a rare and almost uniformly fatal condition, and for the next 1,500 years, almost nothing changed. Physicians could describe diabetes. They could not explain it, and they certainly could not treat it. The next real breakthrough came from a very old-fashioned diagnostic method, tasting the evidence. In 1675, the English physician Thomas Willis noted that the urine of diabetic patients was distinctly sweet and added the Latin word mellitus, honey sweet, to the disease's name, distinguishing it from a separate, unrelated condition called diabetes insipidus, where the urine has no sweetness at all. It took another century for anyone to prove Willis was onto something chemically real rather than just anecdotally true. In 1776, the physician Matthew Dobson evaporated the urine of diabetic patients down to a solid residue and confirmed it was, in fact, sugar, the first hard evidence that diabetes was a disorder of the body's own chemistry, not an imbalance of mystical humors. Through the 19th century, treatment remained almost entirely a matter of starvation. Physicians noticed that restricting a patient's food, especially carbohydrates, reduced the sugar in their urine and could buy them time. The American physician Frederick Allen turned this into a formal, extremely restrictive regimen in the early 20th century, and it worked, in the narrowest sense. Patients on the Allen starvation treatment sometimes lived months or even a couple of years longer than they otherwise would have. But it was not a treatment so much as a controlled decline. Photographs of children on the Allen diet from this era show bodies reduced to skin stretched over bone, kept alive, technically, but starving to death in slow motion, because starving slightly slower than the disease was killing them was the only tool medicine had. The biological picture started coming into focus almost by accident. In 1869, a German medical student named Paul Langerhans discovered clusters of unusual cells scattered through the pancreas, without any idea what they did. They would later be named the islets of Langerhans in his honor. 2 decades later, in 1889, the German physiologists Oskar Minkowski and Joseph von Mering surgically removed a dog's pancreas as part of an unrelated study into fat digestion. Days later, one of them noticed flies swarming around the dog's urine. They tested it and found it full of sugar. The dog, entirely by accident, had developed diabetes the moment its pancreas was removed. The first direct proof that the pancreas was somehow responsible for controlling blood sugar. That set off a race spanning roughly 2 decades to isolate whatever substance inside the pancreas was doing the work. Researchers including Georg Zuelzer, Ernest Scott, and Israel Kleiner all produced crude pancreatic extracts and tested them on diabetic animals, and later on human patients, with real but inconsistent success. Blood sugar would sometimes drop, but the extracts were so impure that they caused fevers, abscesses, and severe allergic reactions. In Romania, the physiologist Nicolae Paulescu developed a pancreatic extract he called Pancrane between 1916 and 1921 and demonstrated that it reliably lowered blood sugar in diabetic dogs. His research was delayed by the First World War and published only in 1921, and he patented the extraction process in Romania the following year. Paulescu came remarkably close to the finish line, close enough that his role in the story remains a point of genuine historical dispute to this day. The team that crossed the finish line first was working out of the University of Toronto. In 1920, a Canadian surgeon named Frederick Banting became convinced he could isolate the pancreatic hormone by tying off the pancreatic duct in dogs, letting the digestive portion of the organ degenerate while preserving the islet cells. He brought the idea to physiologist John Macleod, who was skeptical but offered Banting lab space, 10 dogs, and a research assistant for the summer of 1921, a young medical student named Charles Best. Working through that summer, Banting and Best extracted a substance from dog pancreases that, when injected into a diabetic dog, brought its blood sugar down. It worked. It was also far too impure to safely inject into a human being, so Macleod brought in a biochemist, James Collip, to refine it into something usable. On January 11, 1922, a 14-year-old boy named Leonard Thompson, dying of type 1 diabetes in Toronto General Hospital, became the first person ever injected with the extract. It was still impure. He developed an allergic reaction and showed almost no improvement. 12 days later, on January 23rd, he received a second injection, this time using Collip's newly purified version. The results were almost immediate. His blood sugar dropped to near normal levels within a day. The sugar in his urines disappeared. Word of what had happened in Toronto spread fast, and it reached the families of children who were, at that exact moment, on the Allen starvation diet, slowly dying in hospitals across North America. One of those children was Elizabeth Hughes Gossett, the 15-year-old daughter of United States Secretary of State Charles Evans Hughes. By the time she reached Toronto in 1922, years of starvation treatment had reduced her to under 45 pounds. Banting treated her personally. Within months, she had regained weight, strength, and something close to a normal life, and she went on to live for nearly 60 more years on daily insulin, largely keeping her condition private. Her recovery, documented in detail because of her father's prominence, became one of the most visible proofs the world had that this was not a fluke. It was a cure for the disease's most immediate lethality. The 1923 Nobel Prize in Physiology or Medicine went to Banting and Macleod, and the decision immediately caused friction. Banting was furious that Best had been excluded from the award, given how central his lab work had been, and split his own prize money with him. Macleod, in turn, split his share with Collip. None of the four ever fully resolved who deserved the most credit, and the dispute has followed the discovery of insulin through every history written about it since. What all four agreed on, at least, was what to do next. Banting, Best, and Collip sold the patent for insulin's extraction process to the University of Toronto for a single $1 each, specifically so that no one could monopolize it and price a life-saving treatment out of reach. Banting reportedly said that insulin belonged to the world, not to him. That decision let Eli Lilly and Company begin mass-producing insulin within the year, and by the mid-1920s, a diagnosis that used to mean a slow, visible death by starvation had become a manageable, if demanding, chronic condition. The distinction between what we now call type 1 and type 2 diabetes was formally established in 1936 by the British physician Harold Percival Himsworth, who showed that some patients were highly sensitive to insulin and others were resistant to it. The biological split that Sushruta had noticed by observation, alone more than 2,000 years earlier, without any way to explain it. The decades since have been a steady march of refinement rather than a single dramatic leap. In 1955, the biochemist Frederick Sanger determined the complete amino acid sequence of insulin. the first protein ever fully sequenced. Work that won him a Nobel Prize in 1958 and laid the groundwork for understanding proteins at a molecular level generally. For most of the 20th century, insulin was still extracted from the pancreases of pigs and cows, which worked but occasionally triggered immune reactions in patients whose bodies recognized it as foreign. That changed in 1978, when researchers at Genentech genetically engineered bacteria to produce synthetic human insulin directly, a product Eli Lilly brought to market in 1982 under the name Humulin, the first genetically engineered drug ever approved for human use. Daily life for people with diabetes changed just as dramatically as the drug itself. Portable blood glucose meters in the 1970s let patients test their own blood sugar at home instead of relying on urine tests or hospital visits. Insulin pumps followed shortly after, and continuous glucose monitors and automated closed-loop artificial pancreas systems in the years since have taken over much of the moment-to-moment decision-making that used to fall entirely on the patient. At the same time, a second, very different diabetes epidemic was building. As diets shifted toward processed food and daily life became far more sedentary across the 20th and 21st centuries, type 2 diabetes rates climbed sharply worldwide, and today make up the large majority of that 800 million person global total. In the last few years, drugs originally developed to manage type 2 diabetes by mimicking a gut hormone called GLP-1, semaglutide among them, have triggered another unexpected shift, this time as weight loss treatments reshaping an entire industry, more than a century after Banting and Best first extracted a crude hormone from a dog's pancreas in a borrowed Toronto lab. Put the two eras side by side, and the distance is almost unbelievable. Before 1922, a diagnosis of type 1 diabetes in a child was, without exception, a death sentence measured in months, softened only slightly by slow starvation. After 1922, the same diagnosis is a manageable lifelong condition, and people who receive it can expect to live full, ordinary lives. But the story isn't finished being written fairly. In parts of the world, and even in wealthy countries among people without reliable insurance, insulin, the drug 3 scientists sold for $1 specifically, so it could never be priced out of reach, remains too expensive for some of the people who need it to survive. A century after Frederick Banting refused to put his name on a patent so that insulin could belong to everyone, making sure it actually does is still unfinished work.